just wanted to recap from last week that we kind of worked through some of the basics of Python language, and we worked through some of Python libraries, and we looked at some physics examples like free fall and Newton's law of universal gravity. This week, I wanted to move on to look at some basics of data handling and some basics of data visualization. So we'll look both in today's class and the next class about different ways we can read in data, that we can print out data. We'll also look at different ways that, and this is mostly next class, different ways we can present and plot data. So that's really the topic for this week. In today's class, application, so the assignment is related to, it's actually related to solar dynamos, which are related to the Earth as a dynamo. And so we'll talk a little bit about that, the physics of natural dynamos, but it'll lead us on to looking at some data about solar dynamos and interpreting that data on solar dynamos. So anybody know what an electron, a proton, the Earth, and the sun have in common? Sounds like I'm telling a joke. It's not a joke. Okay, what they have in common is that they're all magnetic. So all the building blocks of, you'd never guess that was the answer. All the building blocks of matter are magnetic, they're little magnets, and actually many of the components of the solar system, the sun and the Earth, are magnetic. And so we're going to talk a little bit about solar magnetism and the Earth's magnetism in today's class. So the Earth and the sun are kind of natural dynamos that produce magnetic fields. What that means is that rotational energy of the sun has a period of like 29 days or something. Rotational energy of the Earth has a period of a day. That rotational energy creates currents and sustains magnetic fields. And so that rotational kinetic energy gets turned into electromagnetic energy. And that's what a dynamo is. If you build a dynamo in the lab or in your office or whatever at home, then you'd be turning kinetic energy into electromagnetic energy. At one level, the Earth is a dynamo, and the sun as a dynamo is quite simple. So at one level in the Earth and the sun, you've got moving charges moving through a magnetic field. So they experience a magnetic force, and that magnetic force drives currents that creates fields themselves. And so that's sort of the physics basis for the Earth as a dynamo and the sun as a dynamo, and the magnetic fields of the Earth and the sun. So on here, this is the first kind of man-made dynamo. And you've probably seen this in sort of introductory general physics class. So this is Michael Faraday's dynamo that he built. So it basically has, if you look here, there's a conducting disk that's rotated. So that's there's rotational energy being put into the dynamo. That disk is immersed in a magnetic field. Here are some of those magnetic field lines. And that disk forms this circuit here. And if you think of a charged particle in the conducting disk, think of an electron in the conducting disk. Any charged particle in the conducting disk is moving. It's over here on the left. It's moving out of the screen towards you. It's moving through a perpendicular magnetic field, vertical magnetic field. So it'll experience a magnetic force, and the magnetic force over here on a positively charged particle will be towards the left, and that force will create a current, will induce a current. And so you can see here that we're turning rotational energy of that we put in by rotating the dynamo into electromagnetic energy. So that's the heart of a dynamo. This one, so Faraday's one, he used an external magnet to create the force and to fill the dynamo. So down here we've got a north pole, and upstairs here we've got a south pole. So the field is coming from some external magnet. But you can use the dynamo itself to create its own magnetic field. So here I slightly modified Faraday's first dynamo, built this self-energizing dynamo. So again, in this one, you rotate this conducting disk here. It's rotating through a magnetic field, which induces a current, the magnetic force law. But that magnetic field itself is created by these windings here. It's due to the current that's being induced in this dynamo. So it's creating its own magnetic field. So it sort of seems a bit like it's a perpetual motion machine, right? That you can't have a perpetual motion machine. But it's not really a perpetual motion machine. You put in some rotational energy, and some of that rotational energy gets turned into the energy needed to sustain the magnetic field. Other energy is used, it gets dissipated as the current flows through the wires. So it's not a perpetual motion machine. It's not breaking the laws of conservation of energy. But you can build a dynamo, and that's what dynamos are at power stations or whatever, that creates its own magnetic field, sustains its own magnetic field. And that's kind of what the Earth and the Sun are. So here's a picture for the Earth. So I don't know how much you know about the makeup of the Earth, but if you started at the very center, there's a solid iron core. Surrounding the solid iron core, there's so that's called the inner core. There's a liquid core of iron, that's the outer core. And then surrounding that is what's called the mantle. So that's sort of silicates and oxides. They're kind of lighter, so the iron's floated to the bottom, and the silicates and the oxides are floated to the top. And then, there's what we live on is this very, very thin crust that sits on the mantle. And so in the Earth, generating the Earth's magnetic field, generating the Earth's magnetism is the same principle as the self-energizing dynamo. So we've got the rotating Earth about some axis. The iron, the liquid iron, is rotating around that axis. In that rotating iron, there's currents. So these yellow curls are currents, and they generate the Earth's magnetic field. And so this arrangement sustains itself. Now, it's a little bit complicated here, but it's not a disk rotating in a magnetic field. It's a sphere, a hollow sphere of liquid iron rotating in the field. And you see these interesting paths that the currents are taking. That's we're viewing this picture as if we're in the Earth's reference frame. In the Earth's reference frame, there will be, I mentioned fictitious forces in, I think, the first class in relation to Einstein's theory of relativity. But in the Earth's reference frame, we would see Coriolis forces. And so these loops are due to Coriolis forces, and these loops create this characteristic magnetic field, this dipole field of the Earth. Okay, so that's just a little bit of introduction. I wanted to say that because on one hand, on one hand, the fact that the Earth has a magnetic field, or the sun has a magnetic field, has a kind of simple explanation. It's this dynamo explanation, that if you have moving charges in a magnetic field, they experience a magnetic force that drives the current. So that's a kind of simple explanation of the Earth's magnetic field, or the solar magnetic field, that we could have discussed in general physics. At another level, the Earth's magnetic field and the solar magnetic field, which is what we'll discuss here, are much more complicated. So the solar magnetic field, for example, exhibits 11-year cycles. And the only way to understand 11-year cycles is through computational physics of the electromagnetic processes and the hydrodynamics in the kind of the solar model. And also we know that the Earth's magnetic field has flipped roughly every 500,000 years over the history of the Earth. And the only way to understand that is the kind of the dynamics of the electromagnetic processes involved and the hydrodynamics of the Earth's core involved. And so at one level, that the Earth is a magnet, that the sun is a magnet, has a simple general physics explanation. At another level, the Earth's magnetic field, the solar magnetic field, exhibits a lot of, there's periodicities, there's chaos in these fields, and that requires computational physics to understand that. And what I've got here, and I've put it here because it's part of the assignment that we're going to meet for today's class, is some data that reflects the solar magnetic field. So the solar magnetic field flips every 11 years. It reverses every 11 years. And one of the clear signatures of the flipping of the Earth's, of the solar magnetic field every 11 years is the number and the pattern of sunspots that we see on the sun as a function of time. So sunspots are just kind of dark regions. Sometimes you can observe them kind of by eye, but the number of those sunspots and the location of those sunspots changes on an 11-year cycle. And these two plots are indicating that. And these reveal kind of the sunspots reflect changes in the magnetism of the sun. And they reflect that, you know, that general physics explanation of the sun as a magnet. It's really much more complicated than that. There's a lot of stuff going on. There's a lot of other periodicities going on. So the bottom graph is just the number of sunspots counted each year over, you know, more than 100 years here. And what you see is there's a periodicity in the sunspots, and this is this 11-year period. And these cycles are given different numbers here. The cycles start back in like 1750 something. That was the first cycle where there was a agreed upon way of counting sunspots. It's quite difficult to come up with a reasonable way to count sunspots. Anyway, we've got 24 cycles from when the data started here. And you see this very strong periodicity in the number of sunspots. So that's part of the 11-year cycle. And that's reflecting that the magnetic field of the sun is changing on an 11-year cycle, and that magnetic field is flipping. North becomes south, south becomes north on an 11-year cycle. This one's called a butterfly plot. So it's time horizontally, on the horizontal axis here. But what you see plotted vertically is the locations of the sunspot with respect to the equator. So right here is the equator, and here we go towards the north pole of the sun, north geographic pole of the sun. Here we go towards the south geographic pole of the sun, and then we're plotting the sunspots, not just their time, but their location. And the different colors indicate, you know, the intensity of the rates of the sunspots. And what you can see here, what's called a butterfly plot, is that if you start off at a solar minimum in the solar cycle of sunspots, when the sunspots start appearing at a relatively large distance from the equator, sun's equator, and as they move towards the maximum, they approach the equator. And then they go to the minimum again. And then you get the same cycle again. Sunspots that are relatively far from the equator, and then they move towards the equator. I should say that sunspots typically always come in pairs. And that's related to the magnetic field. There's magnetic flux that comes out of one and returns into the other. So we're seeing flux bursting out of the surface of the sun and returning into the surface of the sun. And these sunspots kind of don't just vary in time, but they vary in position, reflecting details of the magnetic field in the kind of solar dynamo.